Hello there, and welcome. Tonight, we'll drift toward a galaxy quietly falling into our own. Andromeda is not a distant mystery. It's a future collision in slow motion. Every second, it moves closer. Its stars are brighter, its mass greater, its halo enormous, and within its luminous chaos lie clues about how galaxies grow, merge, and begin again. There are rogue stars, ancient collisions, and strange motions we still don't fully understand. But tonight, we'll uncover them one astonishing fact at a time. And while you're settling in, before your eyes grow too heavy, I'd love it if you gently tapped subscribe or press the little hype button YouTube recently added. It's a small click, but it helps keep these experiments and explorations orbiting out into the algorithm. You can also leave a comment telling me where you're listening from and what time it is in your corner of the night. It's oddly fascinating to see where people are drifting off with us, scattered across the world like stars across the galaxy. Now take a deep breath, let your day drift away, and let's travel together into the quiet corners of the universe. Andromeda floats above us, not as a speck of imagination, but as a real presence in the night. If you stand beneath a dark sky, away from streetlights and towns, you might glimpse it with the naked eye, a faint smudge, soft and stretched, like a thumbprint on black glass. It looks small, but what you're seeing is the light of a trillion stars braided together by gravity, and it's not still. It's moving toward us faster than you can truly feel. A silent descent, steady and inescapable, at 110 kilometers per second. Every moment you've ever lived, every breath you've ever taken, has happened while Andromeda grew imperceptibly nearer. It's not just approaching, it's orbiting with us, caught in a mutual pull, a slow gravitational embrace that has taken billions of years to tighten. We are not falling into Andromeda, and it is not falling into us. We are spiraling toward each other, drawn by mass and momentum, threading our paths through a void that looks empty but is anything but. We are two massive galaxies, spirals full of dust, stars, planets, black holes, and memory on a collision course written in the fabric of space itself. From here on Earth, it's hard to feel that kind of scale. Everything local seems louder. Bills, deadlines, seasons changing, lights going out. But above it all, Andromeda spins, tilted just enough for us to catch its curve. If you could leave the Milky Way and turn around to look back, you might see both galaxies in frame, two radiant disks suspended in blackness, glowing faintly with the light of hundreds of billions of suns, circling each other across a gap of 2.5 million light-years. It sounds like a lot, but in galactic terms, that distance is intimate. Even now, long before the merger, Andromeda's gravity already brushes the edges of our halo. Our galaxy's invisible tendrils made of dark matter and dust are overlapping. They pull at one another like tides. They stretch gas into bridges. They rattle the outer orbits of long-forgotten stars. At the edge of what we can see, the two are already beginning to blend. Andromeda is larger than the Milky Way, not just in the number of stars, but in its mass, its halo, its reach. It carries more weight in the cosmic ledger, and because of that, when we meet, it will shape the outcome more than we will. But this won't be an impact like planets colliding. It will be something stranger. Galaxies are mostly empty space. Even in a merger, almost no stars will actually hit. Instead, their mutual gravity will twist and pull, unraveling spiral arms and warping them into long filaments. Our black holes will circle each other in a dance that could last millions of years, until they spiral inward and become one. Star clouds will be flung into arcs, stellar nurseries will ignite in chaotic waves, and when it's over, the shape will not be spiral anymore. The calm disk of the Milky Way and the tilted arms of Andromeda will stretch and deform, swell and collapse into something new. A single, larger elliptical galaxy, a soft sphere of stars, the spirals erased, replaced by something rounder, redder, and older. We call it Milkomeda, this future shape. The name feels playful, almost whimsical, but the transformation will be profound. Over 5 billion years from now, the sky could look completely different. Instead of the graceful ribbon of the Milky Way stretching overhead, the night could burn with the crowded center of a merged galaxy, brilliant and strange, stars pressed closer than we can now imagine. Some simulations show the solar system being flung outward during the merger, pushed to the outer halo. Others show it riding inward toward the core. No one knows. Exactly. The randomness of cosmic billiards will decide. But wherever we end up, we'll still orbit something, and that something will be the reshaped center of a galaxy that once was two. The first humans looked at Andromeda and thought it was a star. A blurry one. Something close, perhaps. It took telescopes to reveal the truth that it was not a star at all, not even a part of our galaxy. It was another galaxy entirely, filled with its own stars, its own systems, its own possibilities. It took generations to understand that we are not alone in our structure, that the Milky Way is not the universe, and that Andromeda is not just near, it is connected. Now we know it's the closest spiral like us. We know it's bigger. We know it's blue-shifted, meaning the wavelengths of its light are compressed as it comes toward us. Everything else in the universe, almost everything, is red-shifted, drifting away as space expands. But Andromeda isn't going. It's coming. It's not often you can see the future in the sky. Not as a prediction, not as an idea, but as a literal object. When you look at Andromeda, you're seeing the future in slow motion. A story that's already started. A timeline written not in seconds, but in stellar orbits and gravitational flows. You are alive inside that story, tucked into a solar system, orbiting a galaxy that is drifting toward another, already on the path of union. Andromeda won't arrive in your lifetime, nor your children's, nor their descendants. But it's there, waiting, approaching in silence. One day, the night sky will split with its light, but for now, it is just a whisper on the horizon, one spiral drawing closer to another across a quiet, cosmic sea. In the quiet halo surrounding Andromeda, not all stars move the way you'd expect. Most follow the galaxy's rotation, drifting forward along the spiral's natural curve, their orbits aligned like dancers in a slow celestial waltz. But among them are rebels, stars that turn the wrong way. They orbit backward, cutting against the grain like echoes from another rhythm. Their paths defy the logic of a spiral born in symmetry, and yet, there they are, drifting retrograde, serene and silent as if nothing is amiss. These stars are not mistakes, they are not broken, they are quite possibly survivors. Long ago, Andromeda absorbed smaller galaxies dim, ancient companions drawn close by gravity and slowly pulled apart. Their stars, once part of a different structure, were scattered into the larger whole. Some were stripped from their homes in spirals of unraveling light. Others were flung into wide orbits, their original motion preserved even as their systems disintegrated. Now they orbit backward, looping through the halo on tilted paths, wrapped in the memory of where they came from. We can't see the past unfold with our eyes, but we can trace its afterglow in motion. The direction a star moves through space is a kind of fingerprint. It tells a story of birth, of mergers, of long trajectories warped by time. Andromeda's retrograde stars are quiet witnesses to ancient collisions, galaxies that were swallowed whole, their identities dissolved but not forgotten. Each backward-moving orbit is a scar from one of those encounters, faint but permanent. Around Andromeda, star streams arc across the sky like silver ribbons. They're not chaotic, they follow coherent paths, long strands of stars all moving together. These streams are the last visible threads of galaxies that no longer exist, pulled apart by tidal forces. Their stars trail behind them like smoke from a vanished fire. One by one, those galaxies came too close, their shapes distorted, their cores collapsed. Their stars bled outward into the waiting arms of a larger, older galaxy. And even now, those stars continue to orbit, looping slowly around the outskirts of Andromeda, their motion a quiet echo of the galaxies they once belonged to. It's easy to imagine galaxies as whole, complete things, but they are more like cities built from ruins. Nothing stays intact forever. Andromeda is not a pristine spiral. It's a layered construction of mergers and accretions, a tangled history stitched together by gravity. The stars that don't belong are not intruders. They're artifacts, woven into the halo, blending slowly with the rest. Some of these halo stars are older than anything else in Andromeda, more than 12 billion years old. They were born when the universe itself was young, before galaxies had taken full shape, before the elements we know were abundant. These stars formed in environments untouched by metal, their light flavored only by hydrogen and helium. They shine dimly now, low mass and red, but steady. Their lifespans stretch across all of human history, all of Earth's history, and beyond. They have seen everything and changed very little. When astronomers study these stars, especially the ones In retrograde, they look for patterns, chemical signatures, orbital clues, tiny motions that reveal deep truths. By measuring the composition of the stars, we can tell where they formed. A star born in Andromeda itself tends to carry a richer mix of metals, forged in generations of stellar death and rebirth. But stars from smaller galaxies, older galaxies, carry far less. Their light is purer, more ancient. It's like comparing ink on old parchment to fresh print. One carries the wear of time, the other the press of immediacy. Andromeda's halo is full of these contrasts. Stars moving in opposite directions, streams slicing across one another, populations that seem misaligned. It's not a flaw in the structure. It's the story of how the structure came to be. Sometimes, these old stars pass close to the galactic core, looping in from the outskirts like messengers returning home. But most stay far out, drifting in long, slow arcs that can take billions of years to complete. They don't rush. Time moves differently out there. Each orbit is a memory, each path a reminder that nothing stays still forever. Some of these captured stars may even come from galaxies we no longer see at all, shredded so completely that no visible core remains. Only the orphaned stars remain, like debris floating after a shipwreck, pulled into a new current. And yet, despite their differences, over enough time, even these stars will blend. Their orbits will evolve. Their paths will smooth. The halo will thicken and blur until the stars that once moved against the stream now seem part of it. This is how galaxies grow, not in explosions or bursts, but in quiet mergers, slow envelopments, long forgotten folds of time. Andromeda is not a single history. It is many histories superimposed, each layer built from something that came before. And within those layers are stars that should not be there until you realize that this is how galaxies remember. Not in writing, not in song, but in motion and in light. At the center of the Andromeda Galaxy, something strange waits beneath the light. It isn't a single heart, glowing in silence like most galaxies. It's two, twin cores, both shining, both distinct, wrapped in a swirl of stars and gas that doesn't quite settle. One sits close to the center, sharp and bright, while the other is colder, more diffuse, and slightly off to the side, as if it were never meant to be there, and yet refuses to leave. To the naked eye, Andromeda looks smooth, serene, a spiral, as expected. But when telescopes peer deeper, past the arms and the glowing dust lanes, the core reveals a subtle asymmetry. What should be a singular nucleus is split into two bright knots of light, separated by just a few light years, locked in a slow gravitational dance. For years, this puzzled astronomers. Galaxies weren't supposed to have double centers. Not stable ones, not ones that orbited nothing visible. But Andromeda's cores move, not around each other, but around something unseen. Hidden between them is a supermassive black hole, dark, silent, millions of times the mass of the Sun. Though we cannot see it directly, its influence is clear. Stars near the twin nuclei whip around invisible curves at tremendous speeds, tracing arcs that suggest a gravitational source far denser than any cluster of stars could explain. It's not just sitting still, either. The black hole may itself be swaying slightly from the combined pull of the two light sources around it. Nothing is perfectly still in the center of Andromeda. One of the cores, called P1, is brighter and more compact. It looks like what you'd expect from a galactic nucleus, blazing with the density of countless stars packed tightly together. The other, P2, is dimmer and cooler, more diffuse, and offset just enough to be unsettling. It lingers nearby, like a memory that hasn't quite faded, still circling, still glowing, still there. Together, they form an eccentric disk, a kind of elongated orbit of stars swirling around the central black hole like sparks caught in a whirlpool. What could create a structure like this? The best theory we have is merger. Long ago, perhaps billions of years in the past, Andromeda collided with a smaller galaxy. Not a head-on impact, but a glancing encounter, close enough to disrupt, to reshape, to capture. The smaller galaxy's core was pulled in, drawn toward the center of its new host, but it didn't dissolve entirely. Its stars remained clustered, orbiting as a distinct mass around Andromeda's central black hole. And so it lingers, preserved in motion, a fossil in orbit. Galactic mergers are not always clean. Sometimes, galaxies fuse gradually, their stars blending like smoke. Other times, fragments survive, Cores, globular clusters, long tails of disrupted stars. In Andromeda, that surviving fragment may be what we now see as the second nucleus. It's not just a cluster of stars, it's a remnant of identity, a relic of another galaxy's heart now trapped inside a larger one. Over time, stars from both nuclei continue to mix. The central region is slowly smoothing out, but not fast enough to erase the divide completely. When astronomers map the light and motion of stars near the center, they still find signs of that split: the eccentric orbits, the double peak in brightness, the lopsided temperature gradients. Even the chemistry of the stars hints at multiple origins. Some are older, more metal-poor, likely remnants of the captured core. Others are younger, richer in heavy elements, born in Andromeda's own furnace. This strange double heart may not last forever. Given enough time, gravitational friction will gradually dissolve the separation. Stars from both sides will intermix, smoothing the core into something more symmetrical, more expected. But for now, we are seeing a moment in between, a frozen ripple from an ancient encounter. Andromeda's twin cores also raise questions about how common these structures might be. Are they rare, or simply hard to see? Other galaxies, when viewed in enough detail, might reveal similar scars. Perhaps double nuclei are not unusual, just overlooked flickers of galactic pasts hidden behind the illusion of symmetry. There is something haunting about a galaxy with two centers. It suggests a self-divided, a past unresolved. It reminds us that even the grandest structures in the universe carry the marks of collision, of change, of old identities, half remembered. And it reveals, quietly, that galactic evolution is not a smooth ascent, but a process of becoming again, becoming still. When we look at Andromeda's center, we are looking at more than light. We are looking at history layered in orbit, at motion that tells a story, at stars that trace invisible paths around a gravity well too deep to escape. And in that motion, in that unresolved pairing of bright and dim, near and far, we see the echo of two galaxies, two centers, two hearts, beating slightly out of sync, still circling one another in the quiet dark. Surrounding the luminous disk of Andromeda is something vast and unseen. It extends far beyond the glow of stars, past the wisps of gas and the curved sweep of spiral arms. It does not shimmer or cast shadows. It does not block light or reflect it. And yet, it is there, a colossal halo of dark matter, reaching out into space like a ghostly scaffold, invisible to every wavelength we know, but undeniable in its pull. This dark halo isn't just a feature, it is the frame. Without it, the Andromeda Galaxy would fall apart. Its stars orbit too quickly, especially those in the outer disk. According to classical physics, those outer stars should be flung into space, unable to remain bound by the gravity of what we can see. But they don't fly away. They hold their orbits, steady and silent, as if something massive is holding them back, something we cannot see. That something is dark matter. It's not unique to Andromeda. Every galaxy we've studied shows signs of this hidden mass. The stars spin too fast. The rotation curves stay flat, refusing to fall off at the edges like Newton's laws predict. There must be more matter than we can account for. Not stars, not gas, not dust, but something else, something cold, diffuse, and gravitationally potent. In Andromeda, this unseen mass outweighs the visible galaxy by a wide margin. What we see is just the core, glowing faintly at the center of a much larger presence. The halo is enormous. It stretches out well beyond the last star we can trace, possibly as far as 2 million light-years from the galactic center. If you were to chart it, the disk of Andromeda would look like a coin suspended inside a vast sphere, thin and bright against a sea of shadow. Most of the galaxy's mass is in that shadow, more than 90%, by some estimates. We live in the minority, in the part that shines. Andromeda's dark halo is not perfectly smooth. It may be laced with substructures, clumps, and filaments, where dark matter has gathered more densely. Some of these may have once been dwarf galaxies, stripped of their stars but leaving behind their mass. Others could be primordial, dating back to the early universe, formed before stars ever ignited. These clumps bend light from background galaxies in subtle arcs, a phenomenon called gravitational lensing. Through them, we see the imprint of what we cannot touch. Still, most of the halo remains unmapped. We infer its shape from motion, not from vision. By watching how stars and satellite galaxies move, how they accelerate, how they drift, we can sketch the outline of what holds them in place. It's like watching leaves swirl in wind to understand the shape of the air. The pattern is indirect, but real. And the more we study it, the more massive Andromeda becomes. This hidden mass changes everything. It reshapes our understanding of the upcoming collision with the Milky Way. For years, we thought Andromeda and our galaxy were roughly equal. But new estimates suggest Andromeda may be far heavier, thanks to its larger dark matter halo. That difference matters. When galaxies collide, mass dictates momentum. The heavier galaxy bends the path of the other, determines the center of the future system. It decides where the stars will settle, how far they will be flung, and where the merged heart will beat. Even now, dark matter is affecting that trajectory. The two galaxies are already connected by gravity, already spiraling toward one another. Their halos have likely begun to overlap, long before the stars will touch. That invisible connection is tightening with every passing million years, drawing them inward, not through visible threads, but through an enormous gravitational presence we can't yet fully trace. We don't know what dark matter is, we only know what it does. It exerts gravity. It clumps. It shapes galaxies, but it does not interact with light. It does not emit, absorb, or reflect. It moves through ordinary matter with ease, undisturbed and elusive. We've tried to detect it in laboratories, to create it in colliders, to trap it in cryogenic detectors, but it remains beyond our grasp, and yet it is all around us. Not just in Andromeda, but in the Milky Way, in every galaxy, in every cluster. It is the scaffolding of the cosmos. In a sense, dark matter is the true galaxy. The stars, the gas, the radiant arms, those are just the surface, the visible part. The dark halo is the foundation. It's what allows the rest to exist, to spin, to remain coherent across cosmic time. Without it, the spiral would unwind, the stars would scatter. Gravity alone cannot explain the cohesion of a galaxy without the extra mass. With it, everything makes sense. Andromeda is beautiful to the eye, a graceful pinwheel of light and motion, but its true shape is hidden. It is a thing of gravity and silence, of forces we cannot yet name. Its halo may hold clues not only to the structure of galaxies, but to the nature of the universe itself, because dark matter is not just a mystery of Andromeda. It is a mystery of existence. It outweighs the stars, and yet remains unseen. It shapes the galaxies, but leaves no mark. It surrounds us, but we cannot touch it. Somewhere inside that vast halo, stars orbit as they have for billions of years. Dwarf galaxies drift slowly through its outer regions, tugged by forces they do not understand. Light passes through, unbent unless the clumps are dense, and somewhere far inside, Andromeda's luminous core turns like a lantern at the center of a cavern, a flicker of brightness in a sea of darkness. The halo is not empty. It is the structure in which everything else unfolds. The galaxy we see is only the beginning. The real Andromeda lies beyond the light. Andromeda did not become what it is through quiet growth. It became what it is by taking, by pulling smaller galaxies into its gravity, breaking them apart, and folding their remnants into its own vast frame. It is not alone in this behavior. Galaxies, like stars and planets, form and evolve by collecting matter. But Andromeda has done it on a scale we can still see in its structure, in its motion, and in the long, whispering trails of stars that still curve around it like the fading traces of a meal already consumed. It is a galactic cannibal, not a metaphor, but a real and measurable truth. Around the edges of Andromeda, faint rivers of stars stretch like scars, arching across the halo in patterns too ordered to be random. These stellar streams are the remains of dwarf galaxies once whole, now undone. As they passed too close, their stars were stripped away by tidal forces, smeared across the sky in arcs of light that still orbit long after their original forms have vanished. These are the ghosts of galaxies, telltale evidence of past devourings, still drifting in the grip of something larger than themselves. Some of these mergers happened billions of years ago, before the solar system even formed. Others are more recent, still in progress. Andromeda is not finished. It continues to feed, slowly pulling in dwarf galaxies that circle nearby, unraveling them thread by thread. Some, like M32 and M110, are satellites that may have already lost much of their original mass to Andromeda's hunger. Others hover just beyond the reach of its visible disk, fated to spiral inward over the next billion years. One by one, they will be absorbed, and one by one, their identities will be erased. This process is not violent in the way we often imagine. There is no explosion, no immediate collapse. Instead, there is unraveling. Gravitational tides stretch the smaller galaxy as it falls inward, distorting its shape, tugging stars from its edges. The closer it gets, the more it loses. Eventually, what remains is nothing more than a flow of stars, tracing the orbit of what used to be a slow, silent dissolution, recorded only in motion. The evidence isn't just at the edges. Deep within Andromeda's core, its double nucleus may itself be a relic of a galactic merger, a foreign core trapped in orbit around a larger black hole, refusing to fully blend. The halo is littered with stars that move the wrong way, whose orbits tell us they weren't born here. And the chemical signatures of many stars betray different origins, some with compositions richer or poorer than the surrounding populations, shaped in different stellar nurseries under different conditions. When you study Andromeda closely, it becomes clear that it is not a single story. It is a patchwork of many. Even its size is deceptive. The grand spiral we see is only part of the whole. The halo, faint, sprawling, and filled with captured stars, extends far beyond the visible disk. That halo has grown by absorbing the remains of those smaller galaxies. Each one added a little more mass, a little more light, a little more complexity. Over time, the outer edges have thickened with stars that do not belong until they do. Eventually, the memory of the merger fades, and the newcomers become part of the whole. We are not watching history with Andromeda. We are watching something ongoing. It is still growing, still pulling, still reshaping itself through contact. There are stars in its outer regions now that were born in galaxies long since dissolved, still tracing orbits set in motion by past collisions. Some of these streams are immense, arcing hundreds of thousands of light years across, looping like galactic handwriting through space. Others are tighter, shorter, more chaotic, like the last breaths of a system unraveling into its new form. Andromeda's appetite changes what we think a galaxy is. It is not a closed system, not a neat spiral that spins in peace. It is a collector of histories, a digester of structures, a memory made of fragments. Every galaxy in the sky may share this trait, but Andromeda, because of its size and proximity, reveals it most clearly. It is not a singular being. It is a colony of past galaxies, stitched together over time by gravity and chance. In the future, this process will continue. And not just with small galaxies. The Milky Way, too, is on Andromeda's path. And though their eventual merger will be more mutual, more balanced, the process will echo the same pattern. Two large galaxies drawn into one. Stars flung into new orbits. Halos reshaped, histories combined. The galaxy that emerges will not be Andromeda or the Milky Way, but something new built from both, with parts of each still visible if you know where to look. But that is still far ahead. For now, Andromeda continues to consume the smaller things, those nearby companions already caught in its pull. One by one, they come undone, and as they dissolve, their stars become part of something greater. They are not lost. They are transformed. In the dark, quiet sky, Andromeda appears serene, but beneath that calm exterior is a story of absorption, of collision, of long gravitational tides tearing things apart and weaving them back together. It is a galaxy made from others, a cannibal by nature, and its hunger is not yet sated. In the deep silence between galaxies, two spirals move toward each other. Their motion is slow, stretched across billions of years, but it is inevitable. Andromeda and the Milky Way, two great disks of stars, dust, and memory, are on a collision course, written into the structure of space itself. They have been approaching for as long as our planet has existed, and their meeting is not a question of if, but when. From our vantage point within the Milky Way, Andromeda appears as a distant smear of light, drifting serenely in the northern sky. But this faint blur is racing toward us at over 100 kilometers per second, its mass pulling on ours in a vast, silent spiral. The galaxies are already linked by gravity. Their halos may already be touching, distorting slightly as they drift closer, and in roughly 4.5 billion years, they will collide, not like two solid objects slamming together, but like clouds passing through one another, reshaping and stretching in the process. It's easy to imagine destruction, stars crashing, systems exploding, but the reality is stranger. Galaxies are made mostly of empty space. The distances between stars are so vast that even in a direct collision, almost no stars will actually touch. Instead, the gravitational fields will do the work. As the two galaxies approach, tidal forces will begin to distort their shapes. Spiral arms will stretch into streamers. Stellar clouds will be flung outward. Some stars will be ejected entirely, cast into deep space by the violence of the encounter. Our own solar system, quietly orbiting the center of the Milky Way, will be caught in this dance. It's possible that we'll be thrown outward, away from the galactic center, into the stretched and thinning edge of the merger. We may end up in the halo of the new galaxy, circling more distantly, our night sky radically changed. Instead of the delicate band of the Milky Way stretching overhead, we could see brilliant arcs of merged starlight, dense clusters, and perhaps the glowing core of a new, larger structure, something not quite like what we know now. That future galaxy already has a name, Milkomeda, a blend of the Milky Way and Andromeda. It will be something between the two and yet entirely different. No longer a spiral, it will become an elliptical galaxy rounder, older, smoother. Spirals are delicate structures, maintained by motion and symmetry, but mergers break that order. They smear out the arms, scatter the dust, and send stars into more random orbits. The result is a spheroid of light, massive, calm, and redder over time, as new star formation slows and old stars age. Simulations of this event have given us a glimpse of what to expect. They show Andromeda's disk slicing into ours, warping both in spiraling waves. Over the course of several passes, each taking hundreds of millions of years, the galaxies begin to lose their identities. Their central black holes spiral toward each other, eventually merging into a single supermassive core. Rings of starburst activity flare up as clouds of gas are compressed, triggering short-lived periods of new star formation before the fuel runs low. Over time, the chaos settles. The galaxy reshapes. The remnants of two once distinct spirals become a single, blended form. From the Earth's perspective, assuming our planet still orbits the sun by then, the sky would slowly evolve into something unimaginable. First, Andromeda would grow brighter each night, eventually dominating the view, its arms and core stretched across the heavens like a glowing wound. Then, as the galaxies merge, the sky would fill with tangled arcs and clusters, denser and more complex than anything visible now. The concept of the Milky Way would no longer apply. We would no longer be part of a spiral galaxy. We would be residents of something larger, older, and more intricate. And yet, amid all this movement, the sun would likely survive. The planets might remain intact. Life, if it still existed on Earth or elsewhere, could watch the merger unfold over many generations, tracking the slow drift of cosmic structures across the sky. It would not be the end of the world, but it would be the end of our galaxy's form of its spiral arms, its familiar structure, its solitary identity. This is how galaxies grow, not through steady expansion, but through encounters, through collisions, through the long, slow folding of one into another. Andromeda and the Milky Way are not unique in this. The entire universe is shaped by the aftermath of mergers, by the way gravity binds and rebinds matter, drawing it into ever larger structures. Elliptical galaxies that we see in distant clusters are the end products of many such events. Milkomeda will simply be the latest in that lineage, one more node in the branching tree of galactic evolution. For now, the night sky remains mostly unchanged. Andromeda still appears small, the stars still move in their familiar paths, but every second, the distance shrinks. The future is not approaching, it is already underway, and someday, when the two galaxies meet in full, a new galaxy will be born from the ruins of the old. Our home will be remade, not by fire or flood, but by the silent pull of gravity, drawing us into something new, something vast, something beautiful. High above Andromeda's glowing disk, beyond the spiral arms and clusters of bright blue stars, lies a realm of subtle traces and fading echoes. It is the halo dim, immense, and not quite empty. It stretches like a translucent cocoon around the galaxy, far beyond what the eye can see. And within this halo, if you look closely enough, you can find ghosts, not of people, but of galaxies, small, ancient companions that were pulled in long ago and pulled apart even longer ago. Their remains do not shine with the same intensity as living stars. Instead, they ripple faintly through the dark, their forms stretched thin and curved into fragile arcs. These are the stellar fossils of Andromeda's past. To map the outer halo of Andromeda is to study the remnants of galactic memory. Here, the past has not been erased, only diffused. These faint shells and looping streams are the scattered bones of galaxies that once moved freely through space. Each one had its own stars, its own core, its own quiet rhythm. But then they came too close. Andromeda, with its vast mass and deep gravitational well, pulled them in. Their shapes distorted, their stars unspooled, until they were no longer whole. Now, they drift in the halo like chalk lines left behind by vanished tides. Some of these loops are vast, hundreds of thousands of light years long. They twist in slow arcs that trace the gravitational path of what once was. Others are tighter, like the rings left by a stone dropped in calm water. These are not random structures. They follow the rules of motion, revealing the orbits and infall angles of the original galaxies. And in them, astronomers can read a kind of history. Each loop, each ripple, marks an event, a merger, a disruption, a death. Together, they tell a story of how Andromeda grew. When a dwarf galaxy is captured by a larger one, it rarely survives intact. The tidal forces stretch it like soft clay, gradually tearing away the stars from the edges and funneling them into long, curved streams. The core may survive for a while, orbiting like a stone at the center of a ghostly whirlpool. But eventually, even the core dissolves, leaving only trails of stars to hint at what was once there. These remnants are cold and ancient. Their stars are often among the oldest in the universe, still burning dimly billions of years after they were born. In Andromeda's halo, some of these stars are more than 12 billion years old. The structure of the halo is not smooth. It is layered, textured, like a tree trunk sliced open. The outermost regions hold the freshest remnants, stellar streams that still resemble their original forms. Closer in, the loops are older, more diffuse, worn down by time and gravitational stirring. At the center is the galaxy itself, the result of this long accretion, glowing bright but shaped by countless unseen hands. Just as tree rings record seasons of growth and hardship, these stellar shells are imprints of Andromeda's consuming past. In some places, you can see multiple loops overlapping, like the echoes of several songs sung at once. Each wave, each curl, represents a different galaxy torn apart at a different time. Some appear as arcs that bend gently across the sky. Others are like bubbles, nearly complete rings of starlight surrounding nothing. They look delicate, like soap film suspended in the dark. But they are massive, each one containing tens of thousands of stars, each star orbiting in a slow, silent path through the halo. The stars in these streams move differently from those born in Andromeda's disk. Their velocities, their directions, their chemical signatures, everything about them speaks of a foreign origin. Some formed in low metallicity environments, rich in hydrogen and helium, but poor in heavier elements. Others carry traces of more evolved chemistry, depending on how far along their original galaxies were before being devoured. It is possible, by studying their spectra, to match these stars to their long-lost homes. Even though the galaxies themselves are gone, their light still tells their story. The halo is not static. These remnants are still in motion, still orbiting, still interacting. Over time, the loops will fade further, their stars will spread out, blending into the halo's general population. The memories will blur, and the sharp edges of past collisions will soften. But for now, we can still trace them, still follow the lines, still read the signs of ancient violence frozen in the dark. Andromeda's halo is like a palimpsest, a canvas that has been written on, erased, and written on again. Beneath the current galaxy is the memory of others, and those memories are written in stars. There are questions still unanswered. How many galaxies has Andromeda consumed? How long ago did the largest mergers occur? Are their cores still hidden in the halo, darkened but intact, like seeds in deep soil? And what happens when Milky Way's own halo, filled with similar ghosts, finally overlaps with Andromeda's? Will the stories of both galaxies be drawn out, compared, combined? The sky may look still, but it isn't. It is a library of motion, a place where light and gravity have been writing for billions of years. We just need to learn how to read the script. So much of Andromeda's history is not in the arms or the core, but in these wisps and threads barely visible, easily missed, but essential. They are not merely decorations around the edge. They are the record of everything that came before. A halo filled with ghosts, still orbiting in the night. At the center of Andromeda, where the light is thickest and the stars are packed tight like grains of sand, There lies a darkness so dense, so still, that nothing can escape it. Not light, not sound, not even time as we understand it. Buried deep within the core is a supermassive black hole, an object of unimaginable weight and silence, sitting like an anchor at the heart of the galaxy. It is roughly 100 million times the mass of our Sun, far heavier than the black hole at the center of the Milky Way. And yet, from our vantage point, it makes no grand announcement of its presence. No obvious violence, no fireworks. Just gravity and the quiet, shaping of everything around it. It does not consume constantly. For the most part, it waits. But occasionally, it flares. A sudden burst of X-rays, a flash in ultraviolet. These are signs that something has ventured too close, a drifting cloud of gas, perhaps, or a stray star pulled into its grip. As the matter spirals inward, it heats to extraordinary temperatures, glowing fiercely for a brief moment before vanishing forever. These outbursts are rare, fleeting, like a breath in the dark, but they are reminders that the black hole is not dormant, only patient. Once, long ago, it may have been far more active. There is reason to believe that Andromeda's heart once blazed as a quasar, a beacon so bright it could be seen across the universe. In those early, chaotic days, galaxies collided more frequently. Gas was plentiful. Feeding was easy. As matter fell inward, the black hole would have ignited, surrounded by a brilliant accretion disk spinning at relativistic speeds, radiating energy across the electromagnetic spectrum. It would have outshone all the stars around it. For a time, Andromeda may have worn a crown of fire, but those days have passed. Now, the black hole sits in shadow, cloaked by the dense stellar core, its activity reduced to a whisper. The fuel that once poured in is now sparse. Most of the nearby stars are old and stable, their orbits long settled. Still, the evidence of past glory lingers. The mass of the black hole, so much greater than ours, speaks of a time when it fed more greedily, and the twin cores of Andromeda, those two glowing points nestled at its center, may be the fossil record of a merger, the scar of a time when another galaxy, with its own central black hole, joined the dance and changed the rhythm forever. One of those nuclei is colder, dimmer, slightly offset from the galactic center. The other shines brighter, closer to the black hole itself. They swirl in a slow gravitational ballet, each influencing the stars around them. Their paths wound tightly together, like threads of light circling a drain. Between them, the gravity is so intense that stars whip through space at hundreds of kilometers per second, their motions dictated not by the galaxy as a whole, but by this single, central mass. To observe this black hole is not to see it directly, but to watch the way the stars behave in its presence. Like birds circling a predator, their speed gives it away. We measure the Doppler shift of their light, the compression and elongation of wavelengths as they race toward and away from us. From that, we deduce the shape of their orbits, the acceleration, the gravitational pull, and from that pull, we calculate the mass of the thing pulling them. 100 million suns worth, packed into a point no larger than our solar system. Not a star, not a cluster, but something else entirely. There is a strange kind of intimacy to knowing what rests at the heart of a galaxy. All the stars, the spiral, arms, the halos and streams, these are shaped in part by what lies at the center. The black hole is not just a passive passenger. It helps to regulate the growth of the galaxy. When active, its outbursts can blow away gas, halt star formation, reshape the interstellar medium. It is both a destroyer and a sculptor. It feeds, but it also controls. And over cosmic time, it grows in step with the galaxy itself, their fates bound together. Ours is smaller. The black hole at the center of the Milky Way, Sagittarius A times, is a gentle giant by comparison, about 4 million solar masses, still vast, still unfathomable, but dwarfed by Andromeda's core. When the two galaxies merge, their black holes will eventually meet, spiraling around each other in a tightening dance. Their merger will release a burst of gravitational waves, ripples in the fabric of space-time, like the deep tone of a drum sounded once across the cosmos. Afterward, there will be one black hole larger still, seated at the heart of Milkomeda, the new galaxy that will rise from the wreckage of both. But that is in the distant future. For now, Andromeda's black hole waits, occasionally flashing, occasionally breathing, surrounded by stars that orbit in obedience, some in elegant ellipses, others in chaotic sweeps. It is the quiet monarch of a luminous empire, hidden in the very brightest part of the sky. It does not need to shine. Its presence is enough. In a universe filled with light, it is the shadows that sometimes speak loudest. And at the heart of Andromeda, that shadow draws all things inward, quiet, relentless, absolute. On a clear night far from city lights, when the air is dry and the wind is still, you can look up and see something astonishing with your own eyes, without a telescope, without technology, without anything more than darkness and patience. Just above the horizon, near the tilted W of Cassiopeia, there is a soft smudge in the sky. It's not bright, not showy, just a pale, elongated blur, easy to miss if you're not searching for it. But if you pause, if you let your eyes adjust, it appears subtle, ancient, and impossibly distant. That faint blur is Andromeda, a whole galaxy, 1 trillion stars shining together across space, their combined light reaching you through nothing but open air and time. It is the most distant object visible to the unaided human eye, 2.5 million light-years away, a number so vast it breaks free from ordinary scale. And yet, there it is, hovering quietly above you, shimmering with the memory of an era long gone. Because when we see Andromeda, we are not seeing it as it is, we are seeing it as it was. Every photon of light that enters your eye from that galaxy has traveled for 2.5 million years to get here. It left before modern humans walked the earth, before cities, before agriculture, before language, even. The last time this light touched anything solid, Earth was locked in the chill of an ice age. Mammoths roamed the plains. Saber-toothed cats stalked the forests. Our ancestors, wrapped in furs and firelight, may have seen this same blur in the sky and wondered what it was. Now we know. And it hasn't changed. We are not looking across space. We are looking across time. The stars you see are no longer in the same positions. Some may no longer exist. The structure of the galaxy has continued to evolve, rotating slowly, subtly reshaping itself as we watch the past unfold. We are looking at a ghost, an echo of a moment that happened before we knew how to record moments at all. That's part of what makes Andromeda so strange to behold. It's not a vision of now. It's a frozen page from a story that has already moved on. We don't just look up at galaxies, we look back into them. Every galaxy in the sky is a memory. The farther we look, the older the memory becomes, until the deepest reaches of the universe show us a time when galaxies were just beginning to form, when stars were still gathering for the first time. And yet, despite all that distance, Andromeda still touches us. Its light is not theoretical, it's real. Photons, particles of light emitted by stars 2.5 million years ago, are hitting your retina when you look at it. They pass through your cornea, focus on your retina, and trigger an electric signal in your brain. The light that left those ancient stars has ended its journey inside your eyes. You are the final stop for something that has crossed galaxies to get here. If the sky is especially dark, and your vision especially clear, you may begin to see shape in that blur. A faint oval, a hint of rotation. You might notice a brighter core, or imagine the arms stretching out like wings into the black. Most of what you're seeing is not individual stars, but their combined light, an average glow that smooths over the chaos and motion of the real galaxy. It's like looking at a city from far away, where the glow of all the windows becomes one. Even when we're not looking, Andromeda is still there, shining. Its light slips through clouds, through trees, through the high, thin layers of the atmosphere, and only rarely makes contact with a human observer. Most of it goes unseen, scattered into the vastness of space, or absorbed by our sky before reaching the ground. But it never stops coming. A slow, steady river of ancient photons, washing over our planet every night. There's something quietly humbling in that. The galaxy doesn't care whether we're watching. It doesn't need an audience. It simply is. It exists in silence, radiating light born in the fires of 1 trillion suns, sending it out into the dark in every direction. Some of that light finds us, and if we choose, we can catch it on a camera, in a telescope, or simply with our eyes, tilted upward in wonder. It's easy to forget how extraordinary that is. We live surrounded by artificial light, flooded with screens and reflections. Our night skies muted by neon and haze. But when we escape that, even briefly, and let the full depth of the universe come into view, something ancient stirs in us. A memory older than civilization. A feeling that we are not alone, not isolated, but part of a much larger structure, that our sky is not a ceiling, but a window. In Andromeda's light, we see both the past and the future. The past, because its light is so old. The future, because its approach is constant. It is coming closer to us, slowly, invisibly. In another 4 billion years, it will fill the sky not as a blur, but as a blazing spiral stretching from horizon to horizon. Eventually, it will merge with our own galaxy, transforming everything. But tonight, it is just a whisper, a soft breath in the dark, and if you take the time to notice it, to find that dim oval near Cassiopeia and let your eyes linger, you will be doing something rare. You will be sharing a moment with a galaxy across space and time. You will be receiving its light, just as countless others have before you, and for a few quiet seconds, you will be part of something unimaginably vast. Like a monarch moving through the cosmos, Andromeda does not travel alone. Around its massive spiral form, dozens of smaller companions follow, held fast by gravity's invisible tether. These are its satellite galaxies, dwarfs, spheroidals, and faint irregulars moving in slow orbits through the depths of its halo, each one a quiet ember compared to the blazing disk they encircle. They are not arranged in random scatter but form a system of their own, a celestial entourage drifting in the great tide of galactic motion. Some are barely more than clusters of stars, whispering remnants of more complete galaxies, while others shine a little brighter, bold enough to leave their names behind. Among them, 2 stand out more clearly than the rest, M32 and M110. From Earth, they appear like pale smudges just beside the bright core of Andromeda, easily lost in the glow unless you know where to look. M32 is compact and bright, a dwarf elliptical galaxy with a dense core and very little gas. It is strange in its shape, round and tight, almost unnaturally so, as if once it was something more, carved down by time and gravitational stress into a smooth, luminous pebble. It orbits close to Andromeda's heart, and its proximity has left scars. There's evidence that Andromeda may have stripped M32 of its outer stars, pulling away mass and reshaping its form. Yet M32 remains, circling like a defiant remnant of an unfinished story. M110, on the other hand, is fainter and more diffuse, stretched and dimmer, trailing behind Andromeda like a ghost with tattered edges. It too is an elliptical, but with traces of structure, hints of recent activity. Unlike M32, it retains some gas and dust, the lingering fuel for occasional stars to still be born. It seems quieter, more passive, but also less battered by its encounters. Its orbit carries it a bit farther out, and its presence in the sky offers a kind of balance to M32's sharpness. One bright and compact, the other loose and faint. These two are only the most visible pieces of a much larger system. In total, Andromeda is accompanied by at least 50 known satellites, and likely many more still too faint to detect. Some are tucked close, moving quickly in tight orbits. Others swing wide, looping slowly through the outskirts of the galactic halo. They come in all shapes and histories, some rich in ancient stars, others containing strange mixtures of age and metallicity, as if their pasts had been scrambled by collisions or theft. A few show signs of having once been independent galaxies, only recently captured. Others may have always been companions, born in the same primordial swirl of matter that formed Andromeda itself. But what puzzles astronomers most is not their number, it is their alignment. Roughly half of Andromeda's satellites appear to be arranged in a single, remarkably thin plane, like beads strung on an invisible wire stretching across the sky. This arrangement is not just aesthetic, it's dynamic. Many of the galaxies in this formation are not merely lying in the same plane, but also moving together within it, orbiting Andromeda in the same direction. It's a structure too precise to be accidental, and yet too strange to be easily explained. According to standard models of galaxy formation, satellite galaxies should be scattered in 3 dimensions around their parent, like flies around a lantern. Random, diffuse, uncoordinated. But Andromeda's satellites defy that expectation. Their thin, planar distribution suggests a level of order that has no clear cause. Perhaps they are the remains of a single larger galaxy torn apart long ago, its fragments locked into similar orbits. Perhaps they were shaped by some feature of the early universe, a filament of dark matter, a cosmic flow frozen into geometry. Or perhaps we are simply seeing a fleeting moment, a temporary alignment that will dissolve with time. Whatever the explanation, The existence of this satellite plane is deeply curious. It hints that galaxies may evolve through processes even more complex and intertwined than we currently imagine, that there are hidden rules in the cosmic dance patterns not yet understood. And Andromeda, with its sheer size and proximity, gives us our clearest chance to study them. Looking at the satellite galaxies of Andromeda is like watching a family portrait come alive. Each dwarf is a character, a survivor of gravitational tides and cosmic isolation. Some have been stripped of their gas, left barren and dark. Others still flicker with new stars. Some carry the chemical fingerprints of violent pasts. Others bear the soft signatures of slow, quiet aging. Together, they form a constellation of stories orbiting a single, massive presence. Their movements, slow as they are, shape the future of the system. As they orbit, they perturb the stars and gas in Andromeda's halo. They stir the dark matter. They stretch and pull. Over time, some may spiral inward, feeding the central mass. Others may escape entirely, flung away by interactions or gravitational slingshots. The system is not static. It is a living, shifting web of mass and motion. From Earth, it is all barely visible, a few bright spots on the edge of a faint smear of light. But with the right tools, with telescopes and time, we can see more. We can map the orbits, measure the velocities, chart the strange alignment, and in doing so, we catch a glimpse of structure beneath the surface, of a pattern that suggests the universe is not entirely chaotic, that even in the vast, cold dark, there are still symmetries to be found. The satellites of Andromeda do not shine brightly. They do not dominate the sky, but they carry with them secrets about how galaxies grow, how they gather their companions, how they hold them, and how they let them go. And in the quiet arc of their orbits, in the strange flatness of their alignment, we are reminded that even the most familiar galaxies can still surprise us. Even the faintest lights can hold the deepest mysteries. Though vast and ancient, Andromeda is not finished. It wears its age with dignity, its core packed dense with old, yellow stars, its halo threaded with the ghosts of galaxies long since consumed. But scattered across its spiral arms, there are still signs of youth. In the midst of all that quiet maturity, the galaxy still breathes. It still gives birth to stars. This may come as a surprise. Galaxies, like stars, have life cycles. They begin chaotic and bright, forming stars at a furious pace. But over time, the raw material for starbirth, cold gas and interstellar dust, dwindles. Gravity has already done its work, collapsing clouds into suns, triggering waves of formation that sweep through the spiral arms like fire through a dry field. Eventually, the fuel runs low. Star formation slows. The galaxy begins to fade, reddening as its youngest stars burn out and leave behind the older, cooler ones. Many galaxies reach this stage and stay there quiet, red, and dormant. These are called red and dead galaxies. Their skies no longer blaze with newborn light. Andromeda, for all its age, is not one of them. Threaded through its spiral arms, there are still rivers of gas, coiled like smoke through the stars. Dark lanes of dust cross the brighter regions, shadowing the starlight like scars. In these shadows, gravity is still working, pressing particles together, condensing matter into dense knots that will one day ignite. And nestled in the blue haze of the arms are the telltale signs of young stars, massive, hot, and short-lived, their bright blue light betraying their youth. These stars live fast and die violently, burning with incredible intensity before collapsing into neutron stars or exploding as supernovae. Their presence means that Andromeda is still alive in a vital, ongoing way. Some of its star-forming regions are enormous, stretching across hundreds of light years, glowing in infrared as warm clouds of dust cradle embryonic suns. These regions are often invisible to the naked eye but shine brightly when observed through special lenses, revealing a hidden architecture within the spiral arms. They pulse with energy, lit from within by ultraviolet radiation from the newborn stars. And while the rate of formation is not as rapid as in younger, more chaotic galaxies, it is still steady enough to matter. New stars are joining the galaxy. New systems are being born. We can trace this process in the colors of Andromeda. Its arms are still tinged with blue, a subtle glow that reveals where starbirth continues. Between these regions lie older populations, redder, cooler, more settled, but the spiral itself remains defined by contrast. Light and dark, old and new, It is not the frantic frenzy of youth, but the measured, deliberate continuation of a process billions of years in the making. There's a quiet resilience to that. A galaxy that has survived collisions, absorbed neighbors, endured the erosion of time, and still retains the capacity to create. It is not just a record of the past, but a workshop of the present. Somewhere within Andromeda tonight, stars are forming. Gravity is pulling dust into tight knots. Nuclear fusion is sparking to life for the first time. A new sun is burning into existence, surrounded by the raw ingredients of possible worlds. These star-forming regions are not distributed evenly. They trace the spiral arms like veins of fire. Their position and shape are influenced by shock waves, magnetic fields, and the gravitational interactions between stars and gas. Sometimes they appear clustered, as if a burst of formation has been triggered by a passing wave or the lingering echo of an ancient collision. Other times they lie in graceful arcs, wrapping the galactic disk in strands of silver blue. They are the places where the galaxy is still changing, not just passively aging, but actively growing. This activity means that Andromeda is not just a relic, it is still evolving. The stars it forms today will live for billions of years, orbiting through the transformed galaxy that emerges from the coming merger with the Milky Way. They will be part of that future structure, part of Milkomeda. Some may outlive our sun, others may host planets of their own, with skies filled by the light of twin galaxies in collision. The stars being born now could be the ones that illuminate that distant, merged night. And this continuing creation has a role to play in the grand balance of the galaxy. Star formation recycles gas and dust. It stirs the interstellar medium. It enriches the galaxy with new elements forged in stellar cores and supernovae. The presence of young stars helps maintain the spiral structure, adding shape and motion to the great disk. Without star formation, the spiral arms would fade. The galaxy would blur into a smoother, duller shape. But with it, there is still definition, still contrast, still life. Andromeda may one day go quiet. The gas will eventually be spent or blown away. The last great waves of starbirth will end. The blue stars will die first, and the red ones will dim more slowly. In time, the galaxy will glow faintly with the warm light of age, its structure softened, its heart heavy. But that day has not yet come. For now, it is a galaxy that remembers how to create. From our place in the Milky Way, we see it as it was 2.5 million years ago. The light we capture tonight left long before we were here to notice it. Yet even that ancient image shows us a galaxy in motion, lit with the birth cries of stars, still woven with the energy of new beginnings. It is both old and young, both fading and alive. To look at Andromeda is to witness not just the relic of a grand past, but the continuation of something that began long before us and will outlast us by eons. In its dusty arms, stars are still being born, and in those stars, the story continues. Spirals seem like symbols of permanence. They suggest rhythm, order, symmetry. When we look at Andromeda gracefully winding arms stretching outward from a luminous core, it's tempting to believe that its form is frozen, a perfect and unchanging structure suspended in space. But the truth is more fluid. Galaxies are not statues. They are not fixed. Their shapes shift across time, molded by invisible forces, stretched and sculpted by gravity, by motion, by the long echoes of their past. Even Andromeda, majestic and seemingly stable, is slowly, constantly transforming. The spiral arms, those elegant trails of stars and gas, are not static structures. They are not made of the same stars locked in a rigid swirl. Instead, they are like traffic jams in the sky regions where stars bunch together as they orbit, slowed and compressed by gravitational waves that ripple through the disk. As stars move through the galaxy, they drift in and out of these arms. The arms themselves are patterns, density waves that pass through the disk, organizing the stars and gas into visible shape, much like sound waves sculpt air into music. The pattern remains, but the material within it changes. This concept reshapes how we think about galactic form. What we see when we look at Andromeda is not a frozen blueprint, but a moment in a long, fluid choreography. Its stars are all in motion, millions of them sweeping along curved paths, influenced by the collective gravity of the galaxy. Some orbit faster, some slower. Some rise above the disk, while others fall through it. Over time, this movement adds up, reshaping the arms, thickening the core, smudging what once seemed sharply drawn. And within that luminous core lies something else, an elongated structure known as a bar. It's a dense band of stars stretching across the galactic center, connecting the bases of the spiral arms like a bridge of light. Bars are common in large spiral galaxies, and they play an important role in their evolution. They channel gas toward the center, feeding star formation and even the central black hole. They stir the motions of stars, redistributing mass and energy, and they slowly twist and grow, adding new complexity to the shape of the galaxy over time. In Andromeda, this bar is partially obscured from our perspective, tilted at an angle that makes its true structure hard to detect in visible light. But in infrared observations, it becomes clearer, a dense, elongated bulge that hints at a dynamic, evolving core. It is not a flaw or deviation from symmetry. It is part of the natural life of a galaxy, a stage in a long transformation that blurs the lines between spiral and elliptical, between structure and chaos. Mergers and collisions also leave their mark. Andromeda has devoured many smaller galaxies over its lifetime. Each one added stars, gas, and dark matter to the mix, disturbing the existing structure and introducing new patterns. Some of those interactions warped the disk, twisted the arms, or flung stars into the halo. Others helped shape the bar itself, or triggered bursts of star formation that lit up the spiral arms with blue light. These events didn't just decorate the galaxy, they changed it. They wrote new chapters into its form. Even now, Andromeda is still absorbing material. Streams of stars stretch around its halo, remnants of past companions being slowly unwound by gravity. These streams may eventually settle into the disk or dissolve into the halo, but in doing so, they nudge the galaxy's shape. They add motion, asymmetry, complexity. The outer arms shift, the disk thickens. The spiral that once seemed so defined begins to soften, and it is not done changing. In about 4 billion years, Andromeda will merge with the Milky Way. The graceful arms will be pulled and torn, stretched into long tails and bridges of stars. The bar may dissolve or be reborn in a new configuration. The central bulges of both galaxies will collide and mix, and the shape that emerges will no longer be a spiral at all, but something rounder, smoother, an elliptical galaxy born from the ruins of 2 spirals. That future is already set in motion. The shapes we see today are not the final forms. They are waypoints in a long journey of transformation shaped by time and motion more than by any static plan. If you could speed up time, compress 1 billion years into a minute, you would see galaxies pulsing and morphing like living organisms. Their arms would twist, bend, and unwind. Their centers would brighten and shift. Their companions would draw close and be absorbed. You would see that what we call a galaxy is not a shape, but a process. This idea carries a kind of quiet power. It reminds us that nothing in the universe is truly still. Everything changes, even the most massive structures we know. Andromeda, with all its beauty, is not a finished product. It is a snapshot of change and progress, a dance that began long before we were here to watch, and will continue long after we are gone. We see it now with its arms wide, its bar gleaming faintly through the dust, its spiral still intact. But this is only one version of itself. A future observer, millions or billions of years from now, would see something different. They might not see a spiral at all. They might see a sphere of stars, glowing faintly, the memory of a once graceful form hidden in its core. And yet, that too is beautiful, because it tells us that the universe is not rigid or finished. It grows, it adapts, it evolves. Every twist in Andromeda's spiral, every shift in its shape, every ripple in its stars, is part of a much larger story. A story not of stillness, but of flow. In the vast canvas of space, where change unfolds across eons, shape is not a destination, it is a phase, and even the most perfect spiral is only passing through. Beneath the visible surface of Andromeda lies a world we can't see with our eyes alone. To most of us, it appears as a grand swirl of soft light, a pale smear stretched across the night sky, delicate, diffuse, and calm. But that visible light tells only part of the story. Much of what defines Andromeda's present and future is hidden behind curtains of darkness, shrouded in dust and locked inside clouds so cold they emit almost no light at all. What we cannot see is often what matters most. And in Andromeda's case, the true architecture of its evolving structure lives in the shadows. Infrared light opens a secret window into that hidden side. When astronomers turn their instruments toward Andromeda in these longer wavelengths, the view transforms. Suddenly, features once cloaked in silence begin to emerge. Veins of warm dust glow faintly in the arms. Wisps of gas shine where new stars are stirring to life. Entire regions, once obscured behind thick interstellar clouds, light up with the quiet fire of potential. The galaxy becomes a landscape of contrast, not just between light and dark, but between what has already become and what is still becoming. Much of this hidden matter takes the form of cold molecular clouds. These clouds are immense, some stretching for hundreds of light years, and yet they are invisible to the eye, cloaked in dust so thick it swallows starlight. Their temperatures are low, just a few dozen degrees above absolute zero, and their interiors are dense, tangled, and quiet. But within that darkness, stars are born. These clouds are the stellar wombs of Andromeda, the places where gravity gathers hydrogen molecules into tight knots, collapsing them into the bright, burning hearts of new suns. They drift through the spiral arms like phantom rivers, mostly undetectable in visible wavelengths. Only the infrared light, or the signature of molecules like carbon monoxide, can betray their presence. And when astronomers map them, the structure of the galaxy comes into sharper focus. The arms are not just decorative, they are engines of creation. The cold clouds cluster along the arms' inner edges, compressed by the density waves that roll through the disk. When these waves pass, they leave behind regions primed for star formation, like the wake of a ship carving order into an open sea. But even these insights are partial. The dust itself, though it hides so much, also plays a role in shaping what we see. Dust lanes, those dark streaks that cut across the brightness of the spiral arms, are not empty. They are rich in fine particles of carbon and silicate, leftovers from ancient stars. These particles absorb and scatter light, especially in the blue part of the spectrum, causing the stars behind them to appear redder and dimmer. In photographs, these dust lanes seem like scars or fractures across the galaxy's face. But in truth, they are signs of life, of chemistry, of structure and motion. They obscure more than they reveal. Even in our own galaxy, the Milky Way, entire regions remain hidden behind dust. In Andromeda, that effect is compounded by distance. From 2.5 million light-years away, our view is flattened, compressed into a single perspective. The dust thickens that veil. Whole clusters of stars, entire nurseries of formation, may lie behind those lanes, invisible in optical light. And yet, we know they are there, detected by their warmth, by the glow of dust, heated by starlight, or by the faint fingerprints of the molecules they harbor. This interplay of light and darkness adds depth to Andromeda. It is not simply a glowing disk surrounded by halo stars. It is layered. The dust doesn't just float on the surface. It weaves through the arms, embedded in the disk, twisting in strands and filaments, shaped by magnetic fields and gravity. It moves. It reacts. It collapses and disperses. It is both a medium and a memory, a record of past stars and a promise of future ones. Andromeda's dust is also a chemical archive. Within its clouds, heavier elements like carbon, oxygen, and silicon cycle through stages of combination and dispersion. These are the building blocks not just of stars, but of planets, moons, and the molecules that one day might support life. In the cold cores of molecular clouds, simple organic compounds can form, clinging to grains of ice and drifting for millions of years before being swept into the gravity of a forming star system. What begins in darkness may one day burn with light. So much of this story is invisible unless we look in the right way. Andromeda's elegance, the sweep of its arms, the glow of its stars, rests on a hidden foundation. The cold clouds that move through it are quiet and subtle, but they are not passive. They shape the structure. They feed the future. They decide where the next generation of stars will emerge and how the spiral arms will evolve. In their silence, they are powerful, and the dust that hides them, it is not simply an obstacle. It is part of the same cycle. Dust clouds absorb the light of stars, but they also reflect it. They help cool the galaxy, allow clouds to collapse, and protect forming stars from harsh radiation. They play a role in the galaxy's metabolism, regulating energy and motion in ways we're only beginning to understand. To observe Andromeda through infrared eyes is to see it anew, not just as a luminous spiral, but as a dynamic, shadowed organism, a galaxy sculpted not only by stars and gravity, but by the interplay of light and dark. Its beauty is not diminished by the presence of dust. It is enhanced by it. Because in those hidden places, transformation begins. And so, while we gaze at Andromeda and admire its glowing arms and radiant core, we should also remember what lies beneath: the cold clouds drifting in silence, the dust tracing invisible currents, the hidden places where stars are being quietly born. They are the hidden scaffolding of the galaxy, the parts that shape its destiny, even as they remain veiled from view. In the great stillness of space, it is often the unseen that matters most. In the quiet reaches of Andromeda's outskirts, far from the luminous sweep of its spiral arms, there are stars on the run. They don't follow the steady lanes of galactic rotation. They don't drift lazily in the halo like most of their neighbors. Instead, they are outliers, loners with a strange velocity, tearing through space at breakneck speed, disobeying the slow choreography that governs the rest. These are the rogue stars, and some of them are moving so fast they may never return. Their journeys likely began with violence. In galactic terms, collisions don't often mean direct impacts between stars. Space is simply too vast, but gravitational interactions, those invisible handshakes between objects of enormous mass, can hurl stars like stones from a sling. When smaller galaxies are absorbed by giants like Andromeda, their stars are disrupted. Some spiral inward, swallowed into the growing core. Others are flung outward, dislodged from the orderly dance and set loose on long, lonely trajectories. Some may be the remnants of triple star systems torn apart by the pull of a central black hole. In these encounters, one star can be captured, another pulled into a tight orbit, while a third is launched outward with such velocity that it escapes the galaxy entirely. These hypervelocity stars become intergalactic wanderers, one-way travelers threading through the cold, dark, carrying with them the chemical fingerprint of their birthplace and the memory of the force that flung them away. Andromeda shows signs of this same phenomenon. Traces of high-speed stars have been found in its halo, their orbits strange and unbound. Some travel on elongated paths that carry them far from the galactic plane. Others seem to have no discernible pattern at all, just speed and distance, as though caught in mid-flight. These are not the usual motions expected from halo stars, which tend to move in predictable orbits around the center. Instead, they cut across the halo like errant sparks from a dying fire. Detecting them is difficult. The distances involved are immense, and the stars themselves are often faint, old or metal-poor, cast-offs from smaller galaxies long since consumed. But their motions betray them. When observed over time, their paths can be reconstructed, revealing speeds that far exceed the gravitational hold of Andromeda itself. Some may be fast enough to escape not only the galaxy, but the entire local group, a fate shared by only the most extreme of outcasts. It's possible that some of these stars are headed toward us. Given the future merger between the Milky Way and Andromeda, and the complex gravitational interactions already at play, some of these rogue stars may drift into intergalactic space, pass through our halo, or even enter the outskirts of our own galaxy. By the time they arrive, if they do, they will be ancient, perhaps dimming red dwarfs or battered subgiants, stripped of any planetary systems they once held. They will carry no messages, no signs of their origin beyond their unusual motion. What makes them so haunting is not just their speed, but their isolation. Most stars exist in clusters, or in the relative company of a galactic disk, surrounded by dust, gas, and neighbors. But rogue stars are alone. Ejected into emptiness, they become cosmic hermits, their journeys stretching across millions of years without destination or return. They are orphans of gravity, torn from home by forces too large to resist and too indifferent to notice. Andromeda's history is written in such violence. The remnants of consumed galaxies still thread through its halo. Their stars, once members of coherent systems, have been dispersed into streams, shells, and arcs. Some remained tethered, looping around the galaxy in ghostly ribbons. Others, kicked hard enough, slipped away. A few, moving faster than any of the rest, are still being hunted by astronomers, shadows against the night, barely brighter than the space around them, but unmistakably swift. These stars remind us that even the quiet grandeur of a galaxy holds chaos at its core. For all its beauty, Andromeda is not a gentle place. Its arms conceal turbulence, its halo whispers of past collisions, and its gravitational grip, strong as it is, can still lose hold. In the tug-of-war between merging galaxies and the central maw of black holes, some stars are simply caught at the wrong angle, accelerated by chance into the unknown. We don't know how many there are. They are hard to find and even harder to track, but we know they exist. Their presence is not theoretical. It is embedded in the data, in the odd speeds and unusual directions of a scattered few. They are rare, but they are real, and every one of them is a story, a moment when the universe flinched and something was flung free. They challenge our sense of cosmic scale. Galaxies seem like closed systems, islands of matter amid the void, but in truth, they are leaky, porous, and restless. Stars come and go. Tides of motion push and pull across vast distances. Nothing is perfectly sealed, and even the largest structures in the universe have escapees. Somewhere in the night sky, drifting across the black between galaxies, a few of those escapees are still shining, carrying the light of Andromeda far beyond its reach. One of them might be passing overhead right now, silent, ancient, and unseen. High above Andromeda's tranquil glow, the soft arms painted in pastel starlight, the calm sweep of a galaxy we often imagine as serene, there is another kind of radiance, invisible to our eyes, but unmistakable to those who know how to look. It is not soft or quiet. It does not drift gently through space. It pulses, it flares, it burns with the memory of violence. Andromeda, like every massive galaxy, shines in more than just visible light. It glows with X-rays. This high-energy light does not come from ordinary stars. It is born in extremity, in heat and gravity pushed to their limits. Some of it flares from the black hole at Andromeda's core, an object with a mass over 100 million times that of the Sun. Though quiet now compared to its more active past, it occasionally stirs. When matter drifts too close, it heats up as it falls, spinning into a glowing disk of gas that shines furiously before vanishing into darkness. These moments are brief, but their light is fierce. X-rays pour from that inner spiral, tracing the edge of the event horizon, a final signal from matter moments before it is lost forever. Elsewhere in the galaxy, other sources flicker and blaze. Pulsars collapsed, remnants of massive stars rotate like cosmic lighthouses, beaming radiation across space. These dense neutron stars, just a few kilometers wide, can spin hundreds of times per second. Their magnetic fields, millions of times stronger than Earth's, accelerate particles to incredible speeds, creating beams of energy that sweep across the sky. In X-ray, they flash like ghostly metronomes, steady but strange, reminders of cataclysmic deaths that once shook the spiral arms. Binary systems also contribute to the glow. These are pairs of stars orbiting each other, but in some cases, one star has died and left behind a white dwarf, neutron star, or black hole. If the companion star still lives, it may be slowly losing its material stripped by the dead star's gravity. That stolen gas spirals inward, heating up, releasing bursts of X-rays before it vanishes into its partner. These systems are small on a galactic scale, but their energy output is enormous. And when observed in X-ray, they form a constellation of hot points scattered across the disk and halo. The Chandra X-ray Observatory, orbiting Earth in silence, has revealed many of these sources. It peers into Andromeda with eyes tuned not to color or warmth, but to intensity, to the heat of 1,000,000 degrees and beyond. Through its lens, the galaxy appears transformed. No longer a spiral of soft gradients, it becomes a web of high-energy signals, a scatter of brilliant spots in diffuse gas. It reveals not just what shines, but what explodes. Some of these X-ray signals are echoes of past supernovae. When massive stars reach the end of their lives, they collapse and erupt in titanic blasts, flinging their outer layers across space. The shockwaves from these explosions heat the surrounding gas to extreme temperatures, creating glowing remnants that persist for thousands of years. These bubbles and arcs of hot plasma shine brightly in X-ray, marking places where the fabric of the galaxy was torn and reshaped. NuSTAR, another space telescope, extends this view into even higher energies, gamma rays and hard X-rays that pierce deeper into dense regions. With its help, astronomers can study the most energetic events in Andromeda, from black hole flares to the aftermath of stellar collisions. The combination of instruments creates a multi-layered portrait, a galaxy serene in one light, seething in another. What makes this glow so compelling is its contrast with what we see in the night sky. To the naked eye, Andromeda is barely a smudge, a quiet suggestion of something vast and distant, but in the X-ray spectrum, it is anything but gentle. It is a cauldron of high-energy phenomena, of dead stars devouring companions, of magnetic fields twisted to impossible strengths, of matter pushed to extremes. It is not the peaceful spiral we imagine, but a galaxy alive with hidden fire. And this light is not static, it changes. Some X-ray sources flare unexpectedly, growing brighter over hours or days, then fading again into the background. Others pulse with clockwork regularity. Some drift slowly across the sky, carried by the motion of binary systems or the remnants of disrupted galaxies. The glow is not just a backdrop, it is dynamic. It is a language. In studying this radiation, astronomers are also reading Andromeda's history. They can trace past collisions by mapping where hot gas lingers. They can find clusters of compact objects, neutron stars, and black holes that formed in earlier generations of massive stars. They can identify regions of high-energy activity that might have once been galactic cores of smaller galaxies now absorbed into Andromeda's mass. Each flicker in the X-ray image is a story waiting to be decoded. Andromeda reminds us that a galaxy is never just one thing. What we see in visible light is only a fraction of the truth. Beneath the beauty of its spiral arms lies a complex interplay of forces, many of them violent, many of them invisible to our ordinary senses. It glows in soft starlight and in brutal bursts of X-ray, in gentle dust and in plasma heated to millions of degrees. These layers coexist, overlapping, shaping one another. When we look up and find Andromeda in the sky, it's easy to be lulled by its stillness. But hidden in that stillness is intensity. Hidden in that blur of light is a furnace of extremes. And as we build better instruments, as we learn to listen to the universe in more than just one voice, we begin to hear the full complexity of its song. The X-ray glow of Andromeda is not a warning. It is a whisper from the unseen, a reminder that every calm surface conceals a deeper current, and every galaxy, no matter how serene it may appear, holds 1,000 fires burning quietly underneath. In the immense rhythm of cosmic time, even galaxies know seasons. Not in the way we feel them on Earth, where spring blooms and autumn fades in predictable turns, but in a slower, quieter pulse measured in the birth and silence of stars. Andromeda, vast and ancient, moves through these galactic seasons with a grace that belies the forces at play. From a distance, its spiral arms seem eternal, frozen in a moment of spiraling beauty. But over millions of years, change becomes visible. The stars it gives birth to, and the dust it gathers, speak of cycles not unlike our own, though they span eras longer than anything our calendars can hold. There are times when Andromeda's arms flare with youth. Great clouds of gas collapse inward under their own weight, and the galaxy becomes a nursery. Bright blue stars blaze into being, massive and hot, living fast and dying young. These periods are filled with energy. The arms glitter with newborn clusters, regions lit with the glow of hydrogen excited by starlight. In infrared and ultraviolet, these patches stand out vividly, beacons of creation woven into the spiral's tapestry. Then, just as quietly as they began, these bursts slow, the gas thins, the clouds become less dense, the glow fades. The galaxy seems to take a breath. Fewer stars are born. The dust settles. The spiral quiets. Astronomers tracking the star formation history of Andromeda have seen these rhythms written in its light. By studying its stars, especially the older ones, and measuring their age and composition, scientists can reconstruct the pace of its life. They've found signs of intense activity in the past, periods when Andromeda was forming stars more rapidly than it does today. Some of these were likely triggered by interactions with smaller galaxies, which, upon falling into Andromeda's gravity, disturbed its structure and compressed its gas. These galactic collisions, though often long past, left behind waves of stars, like ripples still echoing across a vast celestial lake. But in recent millions of years, the pace seems to be slowing. The rate of star formation has dipped compared to what it once was. It's not a complete stop. New stars are still being born, but it's quieter, more subdued. Some astronomers suggest Andromeda may be entering a transitional phase, shifting from a galaxy in its prime to one slowly winding down. It's not yet a red and dead elliptical galaxy, where star formation has ceased entirely, but it's leaning toward that future. The dust and gas needed for new stars is still there, but not in the abundance it once held. This change doesn't come with fanfare. It happens in shadows, in the dimming of star-forming regions, in the increasing dominance of older, redder stars, in the faint decline of hydrogen emission lines that once blazed from its brightest arms. The galaxy is aging, but it does so with a quiet dignity, drifting towards stillness with a calm that only a structure 100,000 light-years across can possess. And yet, just like Earth's seasons, the process may not be linear. There could be new bursts ahead. Fresh infalls of gas from its halo or from captured dwarf galaxies could reignite regions of activity. Galaxies are never truly isolated. They live in dynamic environments, and their paths cross others over time. The coming collision with the Milky Way may once again stir Andromeda into a frenzy of creation. Compressed gas and gravitational waves could spark a renaissance of light and heat, a return to blazing arms and brilliant clusters. Or it might hasten the opposite, a swift quenching of what little activity remains, leaving behind a merged elliptical remnant glowing with the embers of old stars. In the meantime, the galaxy continues its slow drift toward dormancy. It remains luminous, of course filled with stars already formed, many of them shining steadily for billions of years. From our perspective on Earth, that light is constant. We see Andromeda as a bright smear in a dark sky, a soft blur near Cassiopeia. But that light holds the memory of motion, the fading sparkle of starbirths long since ended, the glow of stars nearing the end of their own quiet journeys. The starlight we see tonight may have come from a cluster born in one of those brighter past seasons, a cluster that now stands alone in a quieter arm. In this sense, Andromeda teaches us that even the most seemingly eternal things change. That stillness is sometimes only a pause. That age brings not only fading, but reflection. And that silence can be beautiful too, not empty, but full of memory. Galaxies do not announce their transitions. They don't shed leaves or tilt toward the sun. But if we listen closely, we can feel the shift. The stars speak in spectra, the dust in infrared, the hydrogen in radio. These are the signs of a season turning. Andromeda's own quiet season may last for hundreds of millions of years. Long enough for civilizations to rise and fall on worlds orbiting its stars, long enough for its spiral arms to twist slightly further, for its black hole to flare again and fall back into slumber. It is a different kind of winter, not one of cold, but of calm, not of death, but of deep rest. And like all seasons, it holds the possibility of change. In the quiet reaches of the Andromeda Galaxy, the stars speak in the language of elements, not in words, or even in light alone, but in the patterns hidden deep within their glow. Every star carries a chemical fingerprint, subtle clues etched in the starlight, telling us where it came from, what it has consumed, and what it might become. These fingerprints vary across the galaxy, drawn like delicate gradients in a painting millions of light years wide. It is through this distribution of elements, what astronomers call metallicity, that we begin to see Andromeda's true history unfold. Not in snapshots, but in layers, like the slow turning of pages in a very old book. At its heart, near the dense and brilliant core, many of Andromeda's stars are ancient. They shine with a quiet steadiness, cool and red, having burned for billions of years. These stars are composed mostly of hydrogen and helium, the raw ingredients of the early universe. They are what astronomers call metal poor, not because they lack iron and other heavy elements entirely, but because they were born before the cosmos had much of those to offer. In the time shortly after the Big Bang, stars formed from simple, pristine gas. Only after many generations of star birth and death supernovae spreading heavier elements outward did the galactic chemistry begin to change. These older stars near Andromeda's core reflect that early state. They formed when the galaxy was younger, more compact, and largely untouched by the interactions that would later sculpt its spirals and swell its halo. Their low metallicity is a mark of time, a fossil of the universe's earliest chapters. And though they may seem quiet now, they are survivors of violent beginnings, witnesses to collisions, black hole flares, and bursts of star formation long faded from view. But as we move outward through Andromeda's disk, toward the spiral arms and star-forming regions, the chemistry begins to shift. Here, the stars are often younger and richer in metals. Their atmospheres contain traces of carbon, oxygen, silicon, magnesium, and iron elements forged in earlier stellar generations and scattered across the galaxy by dying suns. These stars were born from enriched gas, recycled through cosmic time, and their presence maps a galaxy in evolution. The farther from the core we go, the more recent the generations, and the more varied the chemical tapestry becomes. This gradient of metallicity, low at the center, higher toward the edges, is not unique to Andromeda. Our own Milky Way bears a similar pattern, but the exact details, the slope of the change, the specific abundance of each element offer a kind of biography. They tell us how quickly the galaxy grew, how often it collided with smaller neighbors, how vigorously it formed stars, and how thoroughly its gases mixed across epochs. In Andromeda, the pattern suggests a long and complex life, one filled with quiet periods of growth, sudden bursts of activity, and the occasional disruptive merger with a satellite galaxy. Indeed, it's in the outskirts of Andromeda, especially in the halo and tidal streams, where the chemistry grows more erratic. Some stars there are unexpectedly metal-poor, while others carry unusual compositions that don't match the rest of the galaxy. These are likely remnants, shrapnel from smaller galaxies that Andromeda once consumed. Their chemistry is the last whisper of their original identity, surviving long after their structure was torn apart and absorbed into the greater spiral. Each one is a ghost, glowing faintly with stories from a vanished home. Through spectroscopy, we decode these differences. By spreading a star's light into its component colors, astronomers can see which wavelengths are absorbed and emitted. Certain lines correspond to specific elements, allowing researchers to build a catalog of what each star contains. It is painstaking work light that has traveled for over 2 million years, captured and analyzed photon by photon, but it allows us to peer backward through time. Every spectrum is a chapter, every element, a sentence. And across the face of Andromeda, the story grows richer with each line. In places where star formation continues, metallicity is higher still. There, in dusty nurseries glowing faintly in infrared, new stars are being born from clouds seeded with the remains of many ancestors. It's a kind of cosmic inheritance matter passed down through generations, recycled and reshaped again and again. These young stars are built from the ashes of old ones. Their planets, if they form, will contain the raw materials for geology, chemistry, and perhaps even life. And so, the chemistry of Andromeda is not merely an academic detail. It is a map of memory, a record of creation and consumption, of peaceful growth and violent transformation. Each variation in metallicity is a signpost, a point of data that reveals something intimate about how the galaxy has evolved. It is through these measurements that we know Andromeda did not form in one smooth sweep, but through an intricate layering of events, accretion, collision, and coalescence. Even now, Andromeda continues to change. As stars live and die, their chemistry alters the surrounding space. Supernovae continue to erupt, even if rarely, spreading iron and nickel into the void. Stellar winds blow carbon and nitrogen outward. The galactic ecosystem remains in motion, complex and interconnected. From our distant vantage point, we cannot see these changes in real time. But by comparing stars of different ages and regions, we build a kind of time-lapse, one that lets us glimpse how the galaxy came to be and what it may yet become. There is something quietly profound about this, that we can look at a faint, hazy blur in the sky and extract from it such detailed knowledge that, from spectral lines alone, we can reconstruct billions of years of evolution in a structure so vast our minds can scarcely hold it. The chemistry of stars is not just a curiosity, it's a key, and with it, Andromeda opens to us like a book we never knew we could read. Andromeda is a galaxy that reveals itself in pieces, like a puzzle scattered across time. At first glance, it may seem unruly, a sprawling tangle of stars, dust, and memory, shaped by billions of years of motion and collision. A spiral with scars, a core with secrets, tidal streams unraveling into space like frayed thread. To the casual observer, its structure appears asymmetric, warped by ancient interactions, and perhaps forever unsettled. But look more closely. With patience and deeper instruments, and a quiet order begins to emerge. A hidden symmetry, subtle and strange, woven through the chaos. Its spiral arms, for instance, are not perfectly even. One seems broader, the other more tightly curled. Yet when mapped in certain wavelengths, infrared, ultraviolet, even radio, they reveal a surprising balance. The two primary arms mirror each other more than they defy. They echo each other's arcs, tracing complementary curves around the galactic center, like dancers circling the same invisible partner. Their rhythm is not perfect, but it is deliberate, as if the galaxy remembers a time before its outer distortions, a time before collisions pulled at its edges and stirred its stars into waves. Even within those arms, symmetry can be glimpsed. Star-forming regions light up in corresponding locations, dust lanes wind in opposing spirals, and magnetic fields follow patterns that align like invisible scaffolding. It is as if the galaxy is trying to hold on to a blueprint long faded, a structure written into its earliest days and only partly erased by time. Symmetry here is not about exact replication, but about reflection, about a kind of aesthetic memory held in the fabric of stars. Farther out, in the galactic halo, the symmetry becomes more ghost-like. The halo itself is a vast, diffuse sphere of old stars and dark matter extending far beyond the visible disk. It appears chaotic, laced with tidal streams and loops from long-absorbed galaxies. Yet some of these features come in pairs, shells that mirror each other, ripples spaced like echoes, as if something massive once passed through and left symmetrical wakes behind. It's possible that these structures are remnants of ancient mergers, frozen moments from when Andromeda collided with another galaxy and pulled its stars into vast, symmetrical arcs. Like a stone thrown into a pond, the disturbance rippled outward, and those ripples still shimmer, faint but discernible. Even in the distribution of its satellite galaxies, there are hints of pattern. While not perfectly aligned, several dwarf galaxies orbiting Andromeda fall into a thin plane, a strange and narrow sheet of motion, as if they were choreographed rather than scattered. The cause remains unclear. Some believe it to be a relic of Andromeda's formation. Others suspect the ghosts of past interactions. But either way, it's another thread of symmetry hiding in the larger web. This hidden order suggests that galaxies like Andromeda are not merely accidents of matter flung into the dark. There is a self-organizing principle at play, gravity, of course, but also the quiet persistence of balance. Spirals form, not by chance, but through waves of density moving through rotating disks, shaping stars and gas into patterns that echo across billions of years. These spirals can warp, can tilt, can fragment, but they rarely vanish completely. They rebuild, they reassert their rhythm. And in Andromeda, despite all its collisions and cannibalized companions, the spiral endures, its symmetry not broken, but bent. On a grander scale, this symmetry may not be unique. Galaxies across the cosmos exhibit similar hidden structures, resonant bars, mirrored arms, dual nuclei, aligned halos. Some of these patterns may arise from universal physics, others from specific cosmic histories, but in each case, there is the suggestion of a quiet order underneath the visible disorder. A sense that the universe, for all its apparent chaos, leans toward balance, not a perfect symmetry, but a living one, one that adapts, bends, and reforms. For Andromeda, this balance may be temporary. Its future collision with the Milky Way will stretch and twist its structure in unpredictable ways. The spirals may dissolve, the symmetry may collapse. But even then, the resulting galaxy, an elliptical behemoth formed in the union, will likely carry new symmetries of its own, in shape, in motion, in the distribution of stars and the flow of gas. The old order will fold into a new one, and the cycle will continue. And perhaps this is the nature of cosmic symmetry, not static perfection, but evolving harmony. Patterns that form, break, and reform again. Mirrored structures that drift apart and realign. A kind of cosmic breathing. Andromeda, in all its luminous complexity, is not an exception. It is a testament to that balance. Its scars are part of its design. Its asymmetries only emphasize the underlying rhythm. In the slow unfolding of time, it is a galaxy that remembers its shape even as it changes. And in its spiral arms, in its halo echoes, and in the faint alignment of its satellites, we see that memory written not in stone, but in light. In the dark sea of the cosmos, two spiral giants drift silently toward one another, Andromeda and the Milky Way. To the eye, they seem similar, as if cast from the same mold, swirling arms of stars, glowing hearts of light, each with their own families of worlds and mysteries. But when examined side by side, these galaxies reveal differences both subtle and profound. One is heavier, one spins faster, one carries an older heart, while the other holds on to more youthful fire. They are not twins, but more like siblings, shaped by time and circumstance, orbiting quietly toward an ancient, inevitable reunion. Andromeda, known formally as M31, is the larger of the two by almost every visible measure. Its disk stretches more than 220,000 light-years from end to end, nearly double the width of the Milky Way. Through telescopes, we see a sprawling spiral rich in detail. Star-forming arms lined with dust and gas, clusters glowing in blue and gold, and a halo that fades slowly into the black. Our galaxy, though impressive in its own right, appears more modest. Its arms are harder to observe from within, its size slightly smaller, and its shape more hidden by intervening clouds. From the outside, we might look quieter, dimmer, and more delicate, yet size alone doesn't tell the full story. For decades, astronomers believed Andromeda was not only larger but also more massive, home to over 1 trillion stars, compared to the Milky Way's estimated 200 to 400 billion. This would have made it the heavyweight of our local group, the dominant force pulling its neighbors into orbit. But newer measurements of our galaxy's dark matter halo suggest that the Milky Way may contain more mass than once thought, perhaps equal to or even exceeding Andromeda's, depending on how far the invisible halo extends. What we see with our eyes is only the surface. Beneath that, mass is cloaked in gravity's shadows, and then there is age. Both galaxies formed early in the universe's history, shortly after the first stars began to burn. Their central bulges, dense with ancient red stars, whisper of times more than 10 billion years ago. But Andromeda's outer regions may be older still. Some of its halo stars appear to date back over 12 billion years, remnants of the galaxy's chaotic youth when it devoured smaller companions in violent mergers. The Milky Way, too, carries old stars in its halo, and in a mysterious structure known as Gaia Enceladus, a fossil of a galaxy we once consumed. These histories echo one another, shaped by gravity, collision, and time. Their centers are dramatically different. The supermassive black hole at Andromeda's core is estimated to be around 100 million times the mass of the Sun, a behemoth capable of flaring in X-rays and UV as it feeds on nearby matter. Our own black hole, Sagittarius A*, is smaller by comparison, around 4 million solar masses. Though still vast beyond comprehension, it sits quietly by most standards, only occasionally waking with brief flickers of energy. The difference suggests Andromeda may have had a more active past, perhaps even a quasar phase, when its core outshone its entire galaxy. Spin and motion also tell their own tale. Andromeda rotates faster, with stars near its center orbiting at speeds approaching 250 kilometers per second. The Milky Way, slightly slower, still keeps a stately pace through the dark, but more dramatic is their shared movement toward one another. At roughly 110 kilometers per second, Andromeda is closing the gap pulled by gravity across a cosmic void that spans over 2.5 million light-years. They are two great spirals caught in a slow-motion embrace, fated to merge in about 4.5 billion years. When that happens, the differences will blur. The galaxies will pass through each other multiple times, their stars flung into new orbits, their gas clouds compressed into bursts of star formation. Over time, the chaos will settle into a new shape, likely an elliptical galaxy larger than either of its parents. Astronomers have already named this hypothetical future Milkomeda, a fusion of legacies. In it, the distinctions between the Milky Way and Andromeda will vanish. Their stars will mingle. Their histories will merge. Yet for now, their comparison remains a mirror, a way to understand our place by looking outward. By studying Andromeda, we glimpse our own, past and future. We see what happens when galaxies grow too large to remain still. We see the patterns that repeat across space and the variations that make each spiral unique. Andromeda is not just another galaxy. It is our neighbor, our eventual partner in transformation, and perhaps even a reflection of what we might become. Beneath the beauty of its glowing arms and between the stars of its ancient core, Andromeda carries lessons. It tells us that size is fluid, that age is layered, and that even in the vast silence between galaxies, motion never truly ceases. The Milky Way may be smaller or larger depending on what you measure. It may be older in some places, younger in others. But when placed side by side with Andromeda, the picture becomes more complete. Two galaxies, two stories, spiraling in parallel until they meet. And in that moment, everything we compare today will dissolve into one shared identity written across the stars. Across the canvas of the cosmos, the future is always in motion. Nothing in the universe stands still, not stars, not galaxies, and certainly not the space between. Everything is drifting, pulled by gravity's silent hand, bending toward new shapes and new arrangements. The Andromeda Galaxy, with its sweeping arms and ancient heart, is no exception. It is moving steadily, invisibly, toward us. A slow spiral of approach, unhurried but unstoppable. From our place within the Milky Way, it may seem distant and unchanging, a faint smudge in the sky. But every second, it comes closer. Every orbit of our sun, it draws nearer. One day, far beyond our lifetimes, the two great galaxies will meet, and when they do, the night sky will become a stage for something unlike anything our species has ever seen. Astronomers, using the physics of gravity and motion, have simulated that encounter. Frame by frame, they've painted the slow choreography of the merger, not in decades or centuries, but over billions of years. The early moments won't be dramatic to the eye. As Andromeda approaches, it will grow larger in the sky, its spiral arms becoming visible with the naked eye, stretching across constellations where now only darkness lives. Over millions of nights, it will bloom, a flower of stars rising in the east, no longer a faint blur, but a luminous arc. Eventually, the galaxies will begin to overlap. Stars will not crash into each other. There is too much space between them for that, but their gravitational fields will interact. Tides of matter will rise, gas clouds will compress, new stars will ignite, brilliant and blue, scattered like sparks in the galactic dusk. The sky will no longer be the quiet dome we know, but a layered lattice of light, two galaxies interwoven, their arms tangled like ribbons in a storm. From the surface of Earth, if Earth still orbits a star at that time, the view will be sublime. Simulations suggest a sky streaked with radiant arcs, one galaxy cutting through the other, with swirls of star clusters glowing overhead. It will be a sky of motion, always changing. Each night, a new composition. One day, a spiral tilted across the heavens. Another, a vast ring of scattered starlight. The constellations we know, Orion, Cassiopeia, the Big Dipper, will dissolve. They will be overwhelmed by closer, brighter neighbors, stars newly thrown from their ancient paths. And then, as the galaxies pass through each other, gravity will slow them, twist them, and pull them back together again. It won't be a single collision, but a series of encounters. They will swing around one another like dancers, shedding stars and trails of dust. The Milky Way's spiral arms will warp and stretch. Andromeda's structure will distort. Each encounter will steal energy from their orbits until, finally, they coalesce into one. The result will not be another spiral, but a new form entirely, an elliptical galaxy, rounder and softer in shape, with less distinct structure. Some call this future galaxy Milkomeda, a poetic hybrid of its parents. In it, the chaos of collision will settle into stability. New stars will be born from compressed gas. Old stars will find new orbits. Black holes at the centers of both galaxies may merge, forming a larger one that anchors the new core. What will this mean for planets like ours? For solar systems carried along in the arms of the Milky Way? Most will survive the merger. Space, after all, is vast. The distances between stars are so immense that even in a galactic collision, the odds of direct impact are low. But orbits may shift. Some systems may be flung outward into the growing halo, left to drift in the quiet between galaxies. Others may be drawn inward, toward the busy center of the new formation. The sky from those distant exoplanets will look very different, brighter, more crowded, filled with unfamiliar suns. And what of Earth? By the time the merger unfolds in full, Earth may be gone, or transformed beyond recognition. The Sun, 5 billion years from now, will be nearing the end of its life, expanding into a red giant, reshaping the solar system. Our planet may be scorched or swallowed, or perhaps life, if it still exists, will have long since moved on, finding new homes among the stars. But if any observers remain human or otherwise, they will watch this merger with awe, a cosmic event that unfolds not in explosions, but in grace, slow, silent, and vast. In that far-off sky, they will see a truth we can only imagine now, that galaxies are not static things, but phases in a longer flow, that even the grandest spirals bend to time and gravity, that what seems permanent, the stars, the shapes, the silence, is all in motion. The story of Andromeda and the Milky Way is not an ending, but a transformation. It is the cosmos reminding itself that everything evolves. When the last tendrils of the old spirals fade, when Milkomeda stabilizes into its final shape, the night will quiet again, no longer marked by approaching arcs or luminous collisions, but by the steady glow of a new galaxy, whole and complete. And in the long silence that follows, another motion will begin, another drift, another future, written in gravity and light. Long before we had names for the stars, before stories were drawn in the sky and maps etched in the mind, the path was already set. Long before language and light, before biology bloomed and thought awoke, two galaxies were moving toward one another, their destinies drawn not in haste, but in gravity. Andromeda and the Milky Way, two spirals spinning quietly in the dark, separated by millions of light years, yet bound by an invisible thread. Their collision is not a mistake, not an accident of timing or space, but the natural outcome of the way the universe breathes. This is not chaos. It is a slow, deliberate choreography. Every particle, every star, every world caught in a current older than itself. The galaxies are not hurling toward each other in violence. They are drifting patiently, as if drawn together by memory, a memory not of events, but of laws. The quiet rules that shaped the first clusters of matter that gave rise to galaxies at all. Gravity does not rush. It does not shout. It whispers over eons. And this is one of its quietest, most elegant promises. We often think of space as still, as silence hung on nothing, but the truth is motion, constant, unending, and universal. Every star you see is moving, every planet, every atom in your body, and so are you. You, the listener, whether lying in bed beneath a dark ceiling, or walking under a flickering street lamp, or traveling down a quiet road at night, are part of this story. Not a spectator, not apart from it, but a thread in the tapestry. You live inside one of those galaxies. You were born in a world that circles a star that orbits the center of the Milky Way, a center it will one day surrender to, or be reshaped by, when it meets its sister across the void. The entire solar system is adrift, like a leaf on a gentle tide. It spins and moves and changes, not just through time but through space, toward a future written not in months or years, but in billions of revolutions. Andromeda isn't just out there, it's ahead, it's coming, but so slowly, so serenely, that you could live 100,000 lifetimes and still never see it change. Yet the movement is real. If you could rewind time like a film, you'd see the two galaxies separating, further and further apart, until their mutual gravity had not yet taken hold. Fast forward again, and they grow closer, first imperceptibly, then steadily, until they begin to share light, then matter, then identity. You are made of stars, not metaphorically, but literally. The iron in your blood, the calcium in your bones, the carbon in your breath. These atoms were forged in ancient stellar hearts and released in explosions long before Earth ever formed. Some of those atoms may have come from a small galaxy torn apart by Andromeda. Some may have drifted from systems that no longer exist. You are not separate from this cosmic dance. You are one of its echoes. And there is something deeply peaceful in that, because it means the vastness is not indifferent. It is not empty. It is moving with you, through you. The galaxies will merge. Yes, they will become one. And in doing so, they will carry all the histories of their stars, their dust, their mysteries. What seems like destruction is, in truth, transformation. The spirals will blur, but the stars will survive. The sky will look different, but the story continues. We call it fate when we see a path that feels inevitable. But this is older than fate. It is nature at its largest scale. Andromeda will meet the Milky Way because the universe made it so. And somewhere in that story, in that arc of orbits and collisions, you arrived. You looked up. You wondered. You asked where this was all going. It's going here. To this moment in time when we can understand enough to see the shape of our future, to glimpse a billion-year story through the lens of a telescope and the whisper of physics. You are standing on a planet, spinning around a star that's moving through a galaxy that's falling into another. And yet you're calm, breathing, awake, listening. In a way, you are the still point in all this motion, a quiet eye at the center of the cosmic storm. And as galaxies drift toward their embrace, as light stretches and bends and reorders itself around the coming change, you remain brief, conscious, and aware. This is not the end of the story. It's not even the climax. It's one frame in an unbroken reel of time. But for this moment, right now, you are part of it. Part of a universe that dances with itself, part of a galaxy on its way home. We were always on this path,